Alright, so I'm going to explain why we get the best performance or we don't get the best performance out of a duct system. So great performance starts with great design. So if we have a great design, that is a starting point, and great design on a total system, and I don't know if you could zoom in on that, but this is a great design of a balanced system that is going to function properly and perform well. The problem with this diagram is it doesn't give you all the information that you need to build a good duct system. It shows you the layout and it's not explaining as to why, but I'm going to explain as to why now. So the first thing that we have is the layout and where all the ducts are located. That's a map, and that's going to show where the ducts are going to go for the rooms. That's a good start. However, before we got to this level, we had to size all these ducts. It doesn't tell us the sizing on this particular diagram, but it does tell us the layout, which is what we're looking at for right here. So now if we go to this duct, there's a few things that we need to understand. Number one, it's going to be the sizing. Now this is a quick sizing chart, and that quick sizing chart is to give you an idea and a perspective. It is not the sizing chart for this particular system. It's just based on a basic understanding on a quick reference as to what size and what amount of air goes through what size of each duct. So if we're looking here, we're going to measure this, and we're going to see we have a 20-inch by 8-inch duct. So just for a quick reference, we'll go to this size, and we go to the 8-inch column, and then we go to the 20-inch, and we see that this has a capacity to give us 750 cubic feet a minute of air. So everything in this whole section of duct has the maximum capacity, if it's designed correctly, to give us 750 cubic feet a minute of air. But there's something that this chart does not take into consideration, and that is that this duct is lined. When this duct is lined, that means that we have a 1-inch loss on the inside of this side, a 1-inch loss here, a 1-inch loss here. So we do not have a measured length of a capacity of 20 by 8. We have a measured capacity based on the inside diameter of something closer to 18 by 6. So if we look at an 18 by 6 duct, and we go to this chart as a quick reference, and 6 and 18, we have a capacity of 430 cubic feet a minute of air. So that's quite diminished from the 750 that the exterior could hold if it was not lined. So I prefer not to line the ducts for many reasons. One of them is it's greater of a velocity of air because there's less resistance with an unlined duct. And number two, it has a greater capacity to carry more air. And then we would wrap the outside of the ducts with insulation, which this also was wrapped, but there are also some flaws in the way that was done. So the correct way to do this, in my mind, based on the book that tells me how to do this stuff called Manual D, we want an unlined duct, we want an actual measured size, and then we want to seal a duct and then measure and then wrap it correctly. So this duct, when we arrived, was neither sealed nor wrapped correctly, which is indicated by all this black insulation here, all right? So what happened is, if you look at this line right here, it corresponds with this. This is a drive cleat, and this is a slip. This is a trunk line, and this is a reducer. We're starting with a larger size and reducing it down. And this line that correlates with this drive is an indication of where the air was leaking. And we have another drive over here, and we have another line. So that shows us where all the air was leaking out. Now, when somebody designed the system and they would have put it all together on a load calculation, they would have said, okay, we're going to make an assumption that either about leakage, how much do we have or not. So an unlined duct leaks a lot, and it needs to be a larger size. A lined duct needs to be a larger size because we put a liner in and reduce the interior. And so that all needs to be taken into consideration. And then a sealed or an unsealed duct matters based on the loss that we have to the attic. Now, we don't live in the attic. We live in the conditioned space. No occupant lives in the attic. So there's no reason to give the attic any air. So anything that you're conditioning or sending it up to the attic, you're wasting it, and it's not helping anyone. So that's another thing to look at. So other thing we look at is flex duct. So we have this flex duct coming into this metal duct, which is lined, which is reduced to 6 by 18, and that is a flexible duct that's 12 inches, which has the maximum capacity to supply 480 cubic feet a minute of air. And then when we go to our 6 by 18, we have 430. So this duct is supplying, this flex duct is supplying enough air to fill this lined duct. So now, but we have to also understand what from our load calculation do we need at this end. And if we calculate these up, now this is a new calculation based on an air-sealed home and an insulated home. Right now, this house is neither air-sealed nor insulated very well. So we have to take all those things into consideration. So we would need in the closet 4 cubic feet a minute of air, hardly anything, right? We would need in the bathroom 40, so now we have 44. In this room, we need 120. So 120, 160, 164, just to feed this part of the duct system. And then there's another part which needs 203. So 164 and 203 would be 367 cubic feet a minute of air. So 367, we go back to our original of what we have, and we go to this 367, and we have 480. So we have an adequate enough supply for air. But there was something that was not considered here. Originally, this duct had 2 more outlets, and that 2 more outlets also accommodated a closet on the other side, which would have required only another 4. So we still have enough to supply everything that was originally intended to be supplied based on the 12, based on the 20 by 8, which is actually reduced down to 18 by 6. And this system can supply enough air to accommodate the rooms it was designed and laid out to handle. So now, how do we fix what's wrong? Because right now, if we had no duct leakage, all of that air would go to all these rooms and it would be fine. But we don't. So because we're losing a lot of this air and there's no calculation for the loss. And over time, we know this loss has occurred dramatically because of all this black insulation. That means the air blew out with some dirt. The dirt got trapped in the fiberglass. It filtered it out, and it left its mark. So we know that it leaks just about everywhere that there's air flowing through it, and that's going to be this connection, this connection. So these connections we're going to have to seal, and we're going to seal that with a mastic. And that mastic needs to be thoroughly applied to fill in all the holes and gaps to eliminate all the leakage. So it's a little bit harder when we have an existing system, because we have to lift it up and get underneath because it's leaking on the bottom as well. And if you pick it up, you see where all the leakage is because there's all the black lines. So we have to solve that. Another thing that's bad here is that somebody used a really shitty duct connection. And that really shitty duct connection actually fell apart over time. and it wasn't assembled very well. So we had a lot of leakage here that was going to the attic and not to the room. So the rooms could be cold or hot in the summer because they're not getting all the air that they were designed to get. So here are some of the things that we're going to fix. We're going to seal this, and we're going to stop the loss and keep it in the house and not in the attic. These holes were where a duct was originally connected, and somewhere along the way, some rocket scientists had the idea that they were going to take this duct off to give more air someplace else, which is it would never go to. And they took the duct that was feeding probably the closet or something else, and they put this over it. Well, we know that didn't work very well because the tape dried out, the thing fell off, and all the air leaked out of the house. So the air that used to go inside the house through a duct that they disconnected now goes right to the attic. So that's even more ridiculous because people who don't know what they're doing have ideas, and they're not sound ideas. So the things that we're going to do today is we're going to add the original duct connection back. There's another one here for the other part of a room that was disconnected. We're going to add that back. We're going to use a quality connector. So this is a trunk line. This is going to be called a takeoff. This whole takeoff feeds what is called a branch circuit. So we have a trunk with a takeoff and a branch circuit. We want to control how much air goes to each one of these rooms. So this takeoff is going to be an airtight takeoff, and it's going to have a damper on it. So when we do the house correctly downstairs, we know we want 4 cubic feet a minute of air coming out for the closet. We can damper this down to regulate it to only give 4 cubic feet a minute of air. And that'll be regulated and controlled, which it never was before. And this is a horrible job. We're going to take this off. We're going to eliminate, this connection, and then we're going to put another damper on that so that we can get 59 cubic feet a minute of air coming out of that duct system. And this is the goal, is to take a horrible system and make it a high performance system. Can we do it? Yes, because we do have an adequate supply of air, and we do have an adequate supply of ductwork air to feed the rooms that this was designed to contribute to. So that's our goal today. Now, some of the other things that are done wrong in this system is, I didn't explain one thing that I want to explain that's very important. In the design of this system, we will see that we start with a larger duct and then we go to a smaller duct. And the reason that we do that is because when we have each one of these takeoffs of the branch circuits, we're going to lose some of this air. So if we start with a larger size like we do over here, and then we go to a smaller size later, we'll maintain a constant pressure, the same pressure. This is done on a computer, and it's designed so that we can properly design the duct system. So now we're going to take 1, 2, 3 off of the larger size duct, and that reduces the total available amount of air to the rest of the duct. And that total amount of volume of air needs to get a smaller duct size. That duct size is going to go through what's called a transition. So if we look at this over here, we see that we're going to bring this 20 by 8 lined, which is really 18 by 6 lined duct, and we're going to reduce it down to something that is 16 by 8. And if we go back to our chart and we go, okay, we started out with a certain volume over here, 500 or 430, and then we go back to the chart and we would say, what was it? 16 by 8, which is really 14 by 6. And if we go to 6 and 14, that's 320 cubic feet a minute of air. So we're reducing that down because the available amount of air is now less. And it's less because we've already taken, with those 3 branch circuits, some of that air and given it to the rooms. So now we come over here and we still have to supply a bathroom and a closet. And at the very end, we're going to supply another duct because we're going to change the amount, we're going to change the design of where this supplies things to, because it wasn't laid out very good to begin with. So now we have the transition, and we can see that at every transition, this has already been sealed with a lot of gooey mastic, but we no longer have any air leakage. So all the air that we have provided the duct system is still available to be sent down. So it no longer is going to go to the attic, it's going to go to the house, which is the performance that we're trying to get. So we're turning a low performance system into a high performance system. Then that means that, you know, everything that we have designed for is available to us and available to the home. And then when we're all done, we're going to take all this stuff that is now sealed very well, and we're going to wrap it better with insulation and put it all back, because then we're going to preserve more heat. Because if in the summertime this attic is 130 degrees, and in the wintertime this attic is 30 degrees. So by having a greater barrier of separation between the attic through the insulation and the duct system, we also don't have a lot of loss for heat. So we're going to add that too. So when you put all this together, we get a low performance system and we turn it into a high performance system. That gives the customer all the air that they're entitled to, their bills go down, their comfort goes up, and they're going to be more satisfied with how we're doing things in their home. Does that make sense? I think it does to me. So, this is where we're going. Are there any questions about what needs to be done here? So another critical point of design is where we actually put these branch circuits from these takeoffs. Now, if you read the book, which I have read the book in Proper Duct Design through ACA, it tells us we do not want to put any duct takeoffs to start a branch circuit any closer than 2 feet from the very end. So that means we always need 2 feet more of trunk line, which is here. All right, so that's the trunk line that we should have, the last one, before the end of the branch circuit, or the end of the trunk line. And clearly we can see we're beyond that line. So what happens is, in order to maintain equal pressure for every duct and every takeoff from the trunk line, we have to have a place for air to bunch up and push back. And that is 2 feet. This is like 2 inches, 3 inches. So all of the pressure that should be pushing backwards to make sure that this duct is properly pressurized for each branch circuit that comes off is not. It means that this one is going to receive a lot of pressure and it gets to the end, and then it's going to not give enough back pressure here to equally pressurize those ducts. So the performance is going to suffer. So we're going to seal this. We're going to put some mastic on it, and then a piece of metal, and then we're going to put screws in it, and then we're going to put a mastic tape that will not, over time, dissolve into like sugar and crisp stuff. We're going to use a quality product to actually maintain longevity of the system. So this needs to be sealed and put somewhere up here so that we can adequately supply. And we're going to have to make this longer, obviously, so we can adequately supply the area that it's supposed to condition. And then because we have another duct that we're going to relocate and add it to the system, because when we did our numbers, we found out that, oh, we actually have more air in this part of the trunk system than we need. So we're going to take that air and put it to a closer duct system, which will make this use up all the air that it's being distributed. And then this system will perform much better. That system will get more air to it, and the whole system will work and perform a lot better. And you know, while we're down here, just for kicks and giggles, when you look at, we were talking about sealing ducts, right? When you look at sealing a house, this is an area where we have a pipe and a giant hole. So what happens is, and I can actually feel the heat coming up from inside the house and going up into the duct system, and I don't know if we'll be able to see it air or not, but you can actually feel the air blowing up. It's not going to show with this, but coming up out of that hole, and the house is losing heat. We're going to seal that. The insulators are going to seal that. They're going to seal these holes and stop the leakage from the house, so that after this duct puts all the heat down in the house, it stays in the house and it doesn't come back up here. So you know, all that will be done with a different group of guys. So, but it's all part of the home performance in making this home perform a lot better. Because if you don't lose the heat, we don't need to put as much into the house with the duct system. And that just makes everything better. So one thing helps the other. All right.